Hello and welcome, ladies and gentlemen. In this video, we'll be discussing how we can implement multiple linear regression using R. As I mentioned before, this is going to be our last set of videos on R in this course. So I hope you enjoy, and again, I hope you find the methods that we talk about in these R videos to be very useful. These are all methods that I use regularly in my professional statistical practice, and creative use of these accounts for, say, 80% of the statistical analyses that I do on a consulting basis. So these are extraordinarily useful and really do serve as the foundation of everything. In fact, looking back on the course, you can think of the course as the foundational statistics of all different types of analyses. Regression is a fantastic one because essentially what we do with fancier types of analyses, and there's more than this, but a big step is just making fancier regressions, including different types of terms using a little bit of different math that account for different situations. But once you hit multiple regression, again, the door is wide open. So we might have different types of terms than we talked about in this course that could be used, or different things that account for different violations of assumptions and different methods that we can use to address those. But ultimately, this is kind of it. This is kind of the end, is multiple linear regression. And the idea, not the ordinary least squares multiple linear regression calculation method, but the idea behind multiple linear regression actually drives maybe 95 or 98% of research in terms of analysis. So this idea, again, you might not have every term. We've talked about maybe 80% of the content. I should say depends on the context, but a lot of it in terms of foundational pieces. But even the fancier stuff, you're really building that multiple regression, and the interpretation is going to feel very similar, and the implementation is going to feel very similar to this multiple regression stuff. So this last one, I always recommend you pay attention to my videos. I always find them useful, but this last one even more so because of just how useful multiple regression is. So let's get started. As I mentioned before, I'm going to be using a data set from the Datarium package, but first I need to install the package on my computer. And remember, you only have to do this once. Datarium. See if I spelled that right. Yeah, it looks like I did. It'll tell me I can't find this package if I spelled it wrong. So if I did an accidental capital or forgot an accidental capital. After I have that done, I use Control-Shift-C to comment the row my cursor is on, or the highlighted sections. So if you want to comment stuff out really quickly, and then I'm going to load up that Datarium library, and this is where we're going to get started. The head command is really handy when I'm using big data sets because I can just see the first few observations of the data set. And in this data set, you can see I have my YouTube, Facebook, newspaper numbers, and then the outcome we were looking at in the lecture set, the sales. One other thing I can do is the names of the marketing. And if I have a very large or very wide data set, this can be handy because it pulls all of the different column names. And I kind of use this one throughout to remember what are my columns named when I'm writing some of my functions. All right, well, let's talk about the basic regression models that we started the lecture set fitting. So we ran, remember, 3 regression models, one regressing sales on just YouTube, one regressing sales on just Facebook, and one regressing sales on both YouTube and Facebook. So remember, regressing the dependent variable on the independent variable. So here, I'll just quickly run my models, sales on YouTube, and give it my data set marketing. And then I'm just going to copy and paste this. And instead of YouTube, I'll put Facebook. And then I'll copy and paste, or I'll just paste from the previous, and then I'll do plus Facebook. Now, if I did times Facebook, that would do the main effect of YouTube, main effect of Facebook, and the interaction. If I don't want the interaction term, I use the plus sign. So, or yes. If I don't want the interaction term, but I want the 2 main effects, I'll use the plus sign. And I'll be honest, y'all, this is where I got the results. I mean, I ran all the results in our lecture notes in R, so this is where I got them. We had the intercept in YouTube, the intercept in Facebook, and the big point of this, remember, was that the YouTube coefficient is different when it's in the model by itself and when it's in the model with Facebook. And we said, why is that? Well, don't forget, the interpretation changes when you have multiple independent independent variables in your regression model. If you have multiple independent variables in your regression model, the interpretation for YouTube changes to now be the effect of YouTube on sales after accounting for Facebook, or the relationship between YouTube and sales after accounting for Facebook effect if it's a causal relationship based on your study design, relationship if our study design doesn't support a causal relationship. All right, so after that we went to some prediction. And again, we're kind of moving fast in comparison to some of our previous stuff, but remember, we've already talked about fitting models. The only new thing is adding a new variable, and actually, we already did that in ANOVA too. So this is really just kind of combining two things that we've already done, the adding new variables from ANOVA and the linear model, the simple linear regression fitting in R. So for the prediction, all right, so let's go on and make a model, mod1, and I'll call this my one with both variables. So I'm gonna just copy and paste that rather than retyping. Again, I love copying and pasting. If you wonder how I highlight a line, I do Shift End, or if I'm at the end of the line, Shift Home, Control C, and then I just go here. So I use End and Home a lot to get the entire contents of a line pretty quickly. From here, I'm going to go on and make sure I run that so R has that model 1 fit. And then I'm going to do predict. And remember, this is how we did prediction, mod 1. And then I'm going to give it new data, the data frame. So this is all the R syntax that we learned in the simple linear regression. But now, remember, I have two independent variables. And in the simple linear regression R video, we mentioned that R is kind of built for handling multiple independent variables in this data frame. What it does is it requires you to give the name of the variable and then the new number. And so we're going to do that here, but because this is the format that it takes, YouTube equals 175, it can easily handle multiple independent variables. So I want YouTube to be 175. I want Facebook to be, what was it? 30, just 30. Oh, and I can type, I promise. And this is my predicted sales under this condition. We didn't really mention it in the lecture slides, but remember, we can easily do a interval here. So let's say I want a prediction interval. And again, if I'm trying to predict, all right, if I make my YouTube budget this and my Facebook budget this, what will my sales be? Remember, I want a prediction interval, not a confidence interval. Confidence interval is if I did a YouTube budget here, a Facebook budget here, what's the average going to be if I did it a whole bunch of times? The prediction interval is what's the reasonable range that I could expect if I did this once? And actually, remember, prediction intervals sometimes can be wide. Without knowing the context, though, this looks pretty reasonable, 13 to 21. Now, 21 might be a huge gain and 13 is like a moderate gain, but both of these look positive and on a relatively similar order of magnitude as the original prediction, so that's pretty good. One other thing that I've mentioned, and this is probably beyond our scope, but hey, since it's our last R video set, I'll talk about it, is we can give multiple values. So let's say I wanted to do 170 and 170 or 180, let's say. If I give it a vector, remember we use C for concatenate. So now instead of giving it one number, I'm giving it two numbers tied together. And I have to do this for both. I'll do this for Facebook too. And for Facebook, I'll give it 20 and 30. This will actually give me two predictions here. So I can actually do two predictions at the same time and kind of see, okay, I want to look at a couple of different circumstances to see what happens. I can give this, I'm just copying and pasting my prediction interval, and I can get a prediction interval for both of these cases to see what happens. I do this sometimes with clients where I really want to explain a couple of different potential scenarios based on our model. So I model out a few different scenarios, give reasonable ranges for these, and that can be helpful with decision making. All right, one thing we did mention is the joint range. So remember, we don't want to extrapolate. And in the simple linear regression case, we said extrapolation is going beyond the scope of our X variables. But we said when we have multiple independent variables, extrapolation is doing this with the joint range. So what did that mean? Well, think about if I have a data cloud that kind of looks like this. I might have a point down here that's not particularly outside of the range of Y. It's not particularly outside of the range of X, but it never appears in my data set. So even though it's in the range of, excuse me, I shouldn't say Y and X, I should say independent variable 1 and independent variable 2. Even though it's in the range of each independent variable, it never happens for both of those simultaneously. Actually, marketing is a great example here. Typically, if I put a bunch of money into YouTube, I won't also put a bunch of money into Facebook. Or if I put a bunch of money into Facebook, I won't put a bunch of money into YouTube. So say my high value here is YouTube and my low value is Facebook. I might have that. I might have a high value for Facebook and a low value for YouTube, but I'd never have like a high value for Facebook and a high value for YouTube. That is, in my sample, I would never model that situation. So that would actually be outside of the range of my sample. And so if I predict using that, even though each of those values individually might be okay and have been seen, those values together will have never been seen. If I predict doing that, I'm doing extrapolation based on my data, which may or may not be supported. A quick way to check for extrapolation when I have two independent variables is to plot the two independent variables together so I can kind of see what the pattern looks like. And all I do here is plot. It doesn't really matter which one's X and which one's Y. I'll use YouTube, and I'm going to pull the YouTube from column from the marketing data set. Y, I'll do the marketing data set again, and I'll just pull the YouTube column. Or excuse me, the Facebook column. And it doesn't matter which one's Y and X. All I'm doing is plotting these to see what my data values look like. As you can see, this actually looks like a generated data set because this is so nicely distributed. This is a nice little data cloud. There's no missing corners here where my sample didn't represent that. So really anything between 0 and 350 in YouTube and between 0 and 60 in Facebook is supported. But imagine like if this top left corner were blank. In that case, I would never want to do a prediction for a value in this top left corner because I shouldn't say never. I would want to respect and be cautious of a value of prediction in this top left corner because it's never something I saw in my sample. So I'd be predicting something, a case that was never studied in my sample. And in that case, that's called extrapolation, and we just want to be careful of that. One thing that I can do if I am looking at, say, a large graphic with lots of data points and I'm having trouble tracking where my data point is I can use the points command. We talked about this previously in kind of a intuition section in our simple linear regression lecture, and I can put the point on here. So X is YouTube. My X proposed YouTube value is 175. Y is Facebook. My proposed Facebook value is 30. And then I'll make this color equals red, and I'll do a PCH equals 16. That changes. PCH stands for plotting character. Again, R does the open circle. 16 is a closed circle, a fill in the blank. And essentially what I'm going to do is I'm going to put a fill in the blank red dot on this graph to see where my proposed value is. I can see my proposed value is right here, right in the center of all these values. And honestly, it should be because that's how I found this dot. I looked at the center of YouTube, I looked at the center of Facebook and picked this. But that's good to know. That's good to know that this is reasonably represented by my data. I'm not extrapolating when I'm doing this prediction. And this is how I check. Of course, you'd replace your X value and Y value with the corresponding variable that you put, independent variable you put on X, independent variable you put on Y, and the values you're proposing for each of those variables. But if you do this type of plot with your two variables, your two independent variables, this can be a good way to check the joint range of your independent variables and see if the plot you're proposing to do a prediction, or if the point you're proposing to do a prediction for is within that joint range. Again, you want it to be in the data cloud. And if it's not in the data cloud, you get concerned that you're extrapolating. All right, from here, we moved on to matrices. Super happy fun time. So I promised we'd do a little bit of this in R. You do not have to follow along with this, and you're certainly not going to be graded on this. But I think this is kind of fun, and I think you'll find that it's not as hard as it looks. And it might be fun because, you know, we don't actually have to learn matrix math to be able to do the matrix algebra to calculate all of these regression coefficients. We're not going to talk about the standard errors in this course, but I'll show you how using matrices, we can calculate the coefficients for the linear regression model pretty quickly. So we'll do it in just a couple lines. And again, you don't even have to know the matrix math behind it because R is going to take care of all that for you. Kind of fun. All right, so let's get started. How do we do this? Well, first of all, I am going to use capital Y and capital X. So be careful. I'm using capital values for each of these. I won't say that's tradition. I mean, different people use different things for capital values. Sometimes capital letters are used for like the random values and lowercase is for the observed or something like that. In this case, I'm going to use capitals for my matrix representations. And that'll be a vector for Y. So that's going to be my marketing $sales. So if I do capital Y, and again, I'm using capital. If I do lowercase y, it's going to say, hey, I don't know what you're talking about. I'm using capital Y. This is going to be all of my sales. And again, by default, it's not showing this, but it's in one long column. In R, it's treated just as a general vector, and it just lists it like this. But when I get to the matrix multiplication, R is going to treat that as one long column, which is exactly what I want. For X, I'm going to make this is called the design matrix. I'm going to use the cbind command, which combines columns together. And remember, the X, the design matrix, is all of the independent variables listed as columns next to each other with a 1 in the front for the intercept. And again, you don't have to remember this. This isn't super important for you, but if you're interested in seeing where this stuff comes from, again, this is one of the few chances you're going to get to see behind the scenes of, I don't know if you'd call it advanced statistical methods, but maybe you would matrix methods without actually having to learn about matrices. Kind of fun. So this is called the design matrix. I'll look at the top of the design matrix and you'll see it doesn't have the names. It's okay. But this first one's the intercept. This second one is YouTube. That's my first independent variable. And the third one is Facebook. And these will correspond with all of the parameter estimates I'm going to get. The first parameter estimate is going to be for the intercept. The second parameter estimate is going to be for YouTube. And the third parameter estimate is going to be for Facebook. So remember to predict the parameter estimates, my parameter estimates beta hat, and it's going to come out as a vector 1, 2, 3. To predict my parameter estimates, I did X transpose times X. Well, first of all, matrix multiplication, we actually talked about this in a previous video, I think in chi-squared, because we got to take advantage of that to find our expected values. But matrix multiplication is a percent sign times and then a percent sign. This tells R I want to do matrix multiplication, which is a special classification that we're just going to ignore for this class, but go take a matrix algebra course if you're interested in learning more about what it is, or just Google it. Check out Wikipedia. It is kind of interesting, and with small matrices, it'll make sense. With the ones of this scale, we're not going to worry about talking about it because wrapping your head around it's just going to be tough on this, but it's not impossible. So just go check it out. And then I'm also going to do something called a transpose. What a transpose does is it turns all of my columns into rows and all of my rows into columns. So first, let me look at regular X. This is what regular X looks like. Long columns, and then, a bunch of rows and a few columns. And if I do the transpose, each of these columns is now going to turn into row 1, row 2, row 3. So now it's going to go really wide instead of really long. So this is what the transpose of X looks like. R shows this, it goes across and across, and this is where it ends, and it just keeps going across. So this is actually continuing this first line. And if I made the screen wider, it would continue out and out and out and out. This would be 3 rows and 200 columns. So it goes out 200 columns wide. This is just R's representation of that. So it essentially changes this. It takes the matrix as it is in the long form and flips it and rotates it so that all of the columns are now rows. So the first column is now the first row. The second column is now the second row. So our math is the transpose of X, matrix times regular X. And that's it. Now, doing that by hand would take forever, but that's it. So we're just going to ignore that. And again, we're not talking about doing it by hand. Now we need to find the inverse. So to find the inverse of the matrix in R, we use the solve command. So I'm just going to copy and paste that. And this is the inverse of this particular matrix. Now, the cool thing about an inverse of a matrix is when I multiply a matrix times its inverse, it gives me 1 in matrix form. And if you're curious to see what 1 in matrix form looks like, and I know all of you are, I'll go on and do this. Here's our original matrix. I'll wrap it in parentheses. Times, matrix times, the inverse of the matrix, and this is what 1 looks like. That's a little bit confusing. Let me round this so it looks a little bit cleaner. It's 1s on the diagonal columns and 0s everywhere else, and that's the whole point of a matrix inverse. Again, just a fun thing. That's what an inverse of a matrix does, and we're not going to talk about why 1s on the diagonals. Well, 1s on the diagonals are the matrix version of 1, because if you multiply it by anything, it'll give back that original thing. So just like 1 times 2 gives me 2, matrix form of 1 times a matrix form of 2 gives me back that matrix form of 2. So that's why this is considered it's called the identity matrix, but the matrix form of 1. And that's what our matrix inverse is. It's something that when you multiply it by the original thing, gives you back 1. So think about it like dividing by that thing. So like if I take 2 times 1 divided by 2, I get back 1. If I take 5 times 1 divided by 5, I get back 1. So essentially the matrix inverse is like dividing by a number. And remember in our lecture notes, we kind of talked about this. This is kind of like x squared, or the sum of x minus x bar quantity squared. And when we take the inverse of this, it's kind of like dividing by that. And if you look at our regression slope parameter estimate, it did divide by the sum of x minus x bar quantity squared. So it's kind of like what we did with our regular numbers. All right, so from here, I take the matrix inverse of x transpose times x, and then I multiply by x transpose, and then I do a matrix multiply by y. So this was my whole formula, and I get back this. Remember, as we talked about when we looked at the design matrix, the first thing is the intercept. The second thing is the slope as it relates to YouTube. And the third is the slope as it relates to Facebook. So if I compare this to and I'm just going to run this line where I ran the linear model in R to see what this is. Here's my intercept value. Here's my YouTube value. And here's my Facebook value. Cool deal. Here's the cool part. If I take all this, and you don't have to do this, but just to show you, again, this is all for fun anyway, so follow along if you want, don't follow along. I'm going to add a new variable, and I'm going to keep all the math the same. It now gives me another coefficient down here. And if I take my old linear model, I'm going to copy and paste that into here and change it. I'm going to add one more variable down here. I'm going to add newspaper. This now gives me the exact same intercept, the exact same slope, the exact same Facebook, and the exact same newspaper coefficient that I had. All of the matrix math, and actually you can delete these. These are just showing our work. This is the only matrix math I have. All of the matrix math stays the same. I didn't have to change a gal darn thing, but I just added a new variable. Doing this by hand would have been a huge pain, but in matrices, once I have this math set, it stays the same every time. And that's why we really like matrix math. Is this a little bit of a bigger pain than doing it the by hand way for the simple linear regression case? Well, maybe. If you're used to matrices, maybe not. But if you're not used to matrices, probably. But when you get to the more advanced stuff, it's just really, really, really nice. It's kind of worth the learning curve to figure out matrices, so you don't have to change this again. You can use the same equation every time. All right. That's the end of our aside on matrices, but I hope this was kind of interesting to you, maybe to see a little bit of the back end of where all of that comes from. All right, so let's talk about the regression output. This is kind of the built-in function. So I'm going to clear my screen here, and I'm going to do the summary of the mod 1 that we made earlier. So remember, mod 1 is right here. This has YouTube and Facebook. Note that as before, it has my estimates, it has my standard error for each, it has my t-values, and it has my p-values, all of which are extraordinarily highly statistically significant. I have my S if I wanted to build things by hand, my sum of squares, error degrees of freedom, my R squared and adjusted R squared, and my overall F test on this particular model. So I've got a ton of information here. All right. Also, we can do, just like before, the confidence intervals for each of the parameter estimates. That gives me my 95% range. For each of these parameter estimates. You'll note real quick, like again, this is real quick to do when I'm given raw data in R. This takes very, very, very little time, which is absolutely fantastic. It takes very little time. Also, for the ANOVA table, yeah, it does it real quick. I will note one thing about the ANOVA table in R, though. The ANOVA table in R breaks down the ANOVA table by independent variable. Now, if you have a categorical independent variable that you've dummy coded, remember I might have multiple categories and they make dummy coded variables and I put it in. If you just put in the categorical variable in R, R will automatically do dummy codes, though it's going to pick its own reference category. So you got to be careful about that, but it'll automatically create dummy codes. And if you take that approach, when you do the ANOVA, the categorical variable will be included here and will be tested holistically. So that can be kind of handy. For this, though, when I'm looking at this, I don't have the overall test of the model. So in this case, I don't have a full test of all of the independent variables together. If I wanted to do that, I could add the degrees of freedom together here. So yeah, I could add the degrees of freedom, I could add the sum of squares, and I could calculate my own mean squares, F value, and P value using the methods we've discussed in this course. Just go back to your simple linear regression notes and then I'll remind you of how to calculate all these things. And I could calculate the exact F value and P value for the test of all the variables in the independent model. The other thing I could do if I wanted to do that using built-in methods in R, again, the ANOVA by default doesn't do that, but I could do the F test for nested models. We'll talk about that in a moment. So I could do that too if I wanted to, and that would work. All right, speaking of ANOVA, let's go on and talk about some of the ANOVA stuff that we can build out. So remember, sometimes it'll be nice to have the full ANOVA results so that we can do calculations of things like R squared or adjusted R squared. So for this, let's just remind ourselves of how to do this. Remember, I'll need, and I'm going to use my Y. This will be marketing sales. I'm going to need, what else? Y hat. This is going to be the predicted values from the model, and I'll not manually calculate that. I'll use the built-in function to calculate that. I'll need Y bar, and this is going to be the mean of the Y values. And, oh, I am missing something here. I put mean times Y. This is mean open parentheses Y. And maybe I'll just double click these to make sure each of these are reading appropriately. Double click and control enter to run each of these. And yeah, Y is a whole list of numbers. Y hat is a whole list of numbers, and Y bar is a single number. I'm not checking in more detail. I just want to make sure that I'm not doing anything too crazy. For P, I'll need this from my calculations. Remember, P is, in this case, 2. It's the number of independent variables. N is the well, I could do this in a couple ways. I could do the length of Y, or remember my data set is marketing. That's the main data set. I could do however many observations I have using the in row command in marketing. And that's usually what I do when I have a data set in a data frame form like this. Degrees of freedom for regression was P, degrees of freedom for error, and all this is from the simple linear regression notes, because again, the ANOVA table was literally identical because we built it up in the general way in simple linear regression. So I'm just copying all this. Of course, all this is from the multiple linear regression notes too. Remember, we just copied and pasted that in our multiple linear regression. Regression is Y hat minus Y bar, sum of squares regression, quantity squared, and added that up. I'll just copy and paste this. The sum of squares error is Y minus Y hat inside of that, then squared and added up. And then the sum of squares total is Y minus Y bar, all squared and added up. Then I'll just go on and run all these, make sure there's no crazy things going on. I can double check real quick each of these. Again, double clicking and control enter to me is a little quicker. Double clicking just highlights it, control enter runs that highlighted piece. So I'm just running each of these over on the right hand side to see what each of them are. My mental double check, I'm not going to I could compare to the ANOVA table real quick here too, make sure the sum of squares error is 801. Oh, that's interesting. It looks like it's not. Interesting. Sum of squares residual. Oh, yeah, it is. Sum of squares error. This is rounded to 802. The sum of squares regression, we don't have the sum of squares regression because remember, YouTube and Facebook are listed separately, whereas this is listing them all together. So this would be how I could look at the overall test as well as I could just manually calculate the sum of squares regression. And you'll note, again, these calculations, once we've got the hang of how we put these pieces together, are really, really quick. Again, doing this by hand, each of the y hats minus y bars, this is how many of those differences we'd have to do. And then we would have to square, raised to the second power, each of those differences. That's a huge, huge, huge pain. This is really impossible to do by hand. But in software, this is just so quick to do. Not only to do all that, but then to add up all the results as well. So this is very, very, very possible and very, very, very quick to do by hand if I wanted to build this out. And then from here, I could do my mean squares regression, and maybe I'll just do that to put this together, sum of squares regression over the degrees of freedom regression. And then my mean squares error is the sum of squares error over the degrees of freedom error. And then I'll build out my tests. So my F statistic, MSR over MSE. So this would be the test of all of the things together. Again, this is the one that R doesn't give us with the ANOVA table. My critical value, if I wanted that. Remember, this is the F distribution. I'll use an alpha of 0.05. Degrees of freedom 1 is the numerator, so degrees of freedom regression. Degrees of freedom 2 is the denominator, so degrees of freedom error. And then lower dot tail equals false. So this is my cutoff. I see with my test statistic. My test statistic is way bigger than the cutoff. So here's my cutoff, and my test statistic is through my wall over here. So we've got a huge test statistic. This is significant. That is, there is enough evidence to believe that at least one of the things has an effect. We came in believing nothing has an effect, and we've changed our mind. This was enough evidence to change our mind. The data under the belief that nothing has an effect, that's where I calculate my critical value. The data are just ridiculous under that belief. And so we're going to change that default belief. We're going to change our mind and say, okay, well, maybe there is an effect. And then we can go through and test each of these individually to see where the effect is. Is it with YouTube? Is it with Facebook? Is it with both? And in this case, it's with both. For the p-value for that, I would do, because this is not a two-tail test, always a top-tail test with the F here. I would put in my test statistic, and remember I'm using the F notation for my test statistic. Degrees of freedom 1 is still the numerator. Degrees of freedom 2 is still the denominator. R is the numerator, regression. E is the denominator. Lower tail equals false. This is my p-value. Good freaking gracious. We're like breaking math here with how small that p-value is. So a very, very, very small number. Actually, I wonder, remember we can use that format command. I think we might break the format command with this one. Remember, I just copy and paste it in as the first argument. Then I do a comma, write scientific equals false. This is how many leading zeros there are. Oh, that's fun. I'm glad we did this. This is how many leading zeros there are for that p-value. 98 of them. I guess you can count if you want. I'm just gonna trust it. That's a very, 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 very small p-value. Actually, I'll say I actually think this goes below the scope of accuracy calculated by computers. So this is probably not exact. But it is pretty funny. What is exact is that it's very, very, very small. For our purposes, small enough to reject the null hypothesis. All right, let's talk about the coefficient of determination. Remember, R squared, the formal term for that is coefficient of determination. Remember, this is just the sum of squares regression over sum of squares total, and we calculated those above. Not too bad to calculate them. This is included in my summary of my model. It's right here, the multiple R squared. I can see that here out to a few more decimal places. So I'll call this R underscore SQ for R squared. And actually, I'll use a capital R. We use a lowercase r sometimes with simple linear regression because it is just the basic correlation, which is lowercase r squared. But with multiple regression, typically we use capital R squared. Now for my adjusted R squared, remember the formula, and I'm just looking at my notes here. 1 minus open parentheses, 1 minus r squared, this value from above. And again, I'm putting a capital R as always in this course. And gosh, aren't you going to get excited that I don't say this anymore? But remember, you can copy and paste the number in here if you don't want to use variables. Always an option. And then I'm going to multiply, and this is going to be a fraction, so I'm going to do my trick where I do open parentheses divided by open parentheses, and I'm wrapping all of this in parentheses. I probably don't need to, but I just want to make sure I'm doing this division before I'm multiplying by this 1 minus r squared, and then I'm doing the 1 minus r squared before I'm doing any multiplying or subtracting here. So I just want to be really clear, so I'm using so many sets of parentheses. I had n minus 1 in the top, and in the bottom I had n minus p minus 1. And because I defined n up here, the number of observations I had, number of rows in that data set, and p as 2, this is all set to run. R squared was my 0.8971, which we calculated right here, sum of squares regression over sum of squares total. And that makes my R squared adjusted. I'll call it RSQ underscore ADJ. You know, we don't really need to name this. We're never going to use this again. But my R squared adjusted is this, what is it again? That's kind of a long name. Maybe that's too awkward. 0.8961 or 0.8962 rounded to 4 decimal places. Checking here, I see that's also included in my summary of the model. Not only the original R squared, but also the adjusted R squared. And this is the calculations by hand based on our ANOVA table. All right. Well, let's kind of close out this video, and then we'll pick up with some other stuff. But let's close out this video with the comparison of nested models. So remember, with nested models, what I do is I have a full model that has all of the variables in it, and then a reduced model where I take out the variables I'm interested in. I don't take out everything other than the variables I'm interested in. I take out the ones that I'm interested in. And the idea is, hey, if I take out the stuff I'm interested in, does it do worse? So think about, you have your favorite sports team and somebody says, oh, so-and-so isn't that good. And you're like, all right, well, let's just drop him from the team and see how good your team does then. And then if the team fails, then that person has to say, well, yeah, maybe we do need him on the team. But if the team keeps doing great, well, maybe you didn't need that player on the team. So in this case, I'm going to do my full model, and I'm going to do the one with all 3 of the variables. So in this case, I'll call this full underscore mod. LM, I'll do sales, squiggle, market, or excuse me, YouTube, plus Facebook, plus newspaper. I will note I'm not looking at any interaction terms here. You can do interaction terms in these types of tests. I'm kind of ignoring them, but remember, that does make a statistical assumption that there are no interaction terms. So just a side note, it's not something to stress about for here, but just note that that is going on behind the scenes. All right, now I'm going to do a reduced model. So let's say I want to test variable 1 and 3 together. I want to test the joint contribution of YouTube and newspaper. Note, with such a test, I'm not going to be able to tell which one is it that contributes the most. I'm just going to say, I want to test the joint contribution of these things. Remember that this is a fantastically useful analysis if I have categorical data with dummy-coded variables, where I can pull out all the dummy-coded variables associated with that particular categorical variable to do a test of the variable as a whole. I also use this very often professionally when I'm doing an analysis of, say, variables above and beyond demographic information. And I want to say, no, this contributes above and beyond a person's socioeconomic status, or this contributes above and beyond a person's previous GPA. So I'd include all those variables for the demographics or for the baseline to start, and then I would run the analysis, and I'd do one of these analyses to say, these independent variables, the ones that I care about, contribute as a group above and beyond this baseline group of variables. So I'd run the model with all of the variables in it, then I'd take out the ones that I'm interested in, leaving in only the demographics, and then hopefully the model would show when I take out the ones I'm interested in, the reduced model is now worse, significantly worse than the full model. So anyway, this is how we build our models, full and reduced model. You can look at these if you want. The full model is just a model with all of them in, and the reduced model is just a model with not all of them in. Oop, except I didn't take them out. So, yikes, I got to take out the ones I'm interested in, 1 and 3. Let's try that again. The reduced model is the one without the ones in there, so good thing I checked, I guess. And then to run this analysis, I use the same ANOVA command that I used before. So this is, in a way, an analysis of variance. This is an F test. This is an ANOVA, but I'm using this ANOVA command. Now I'm going to feed it, instead of just one model, which would give me the ANOVA table for that model, I'm going to feed it both. I'll give it the reduced model first, and then I'll give it the full model. And let's look at the output here. Let's clear the screen. Here's my output. What I have here is the first model, the reduced one, the second model, the full one, and it does my analysis of variance. It looks at my residual sums of squares, or the sum of squares error for each one. It calculates the degrees of freedom. Remember, in our case, the change in P, or delta P, was the first degrees of freedom in the F statistic. And in this case, that's 2, and that matches up here. I took out 2 variables. The degrees of freedom for this test should be 2. Calculates my F value and the P value for that comparison, finding these variables, which I took out, to contribute statistically significantly, highly significantly, to the model. What does that mean? That means that, well, first of all, the one without these variables does worse than the one with these variables. What does that mean interpretationally? It means these variables do something. If things without them are doing badly, and then I put them in and they're doing well, that means these variables are contributing to that outcome. Again, is it one? Is it newspaper? Is it YouTube? Is it the combination of the two? This doesn't tell me that. Just like with ANOVA, it didn't tell us which factor level was the one, which factor levels were different. In this case, this doesn't tell us which of the independent variables are contributing significantly. Could be one, could be the other, could be both. But this does tell us that the group of independent variables that I took out to test are significantly contributing. My results indicate that the combination of YouTube and newspaper marketing strategies significantly contribute to the number of sales I'm seeing. And that's how I use my nested models. Alrighty, team. Well, in this video, we began our implementation of multiple linear regression in R. We talked about a lot of stuff. We talked about doing our basic regression models, doing some prediction, looking at the joint range for prediction, doing all this in matrix form, which was just a bit of fun, but hopefully you may have found it interesting that we can do all this, and this is actually how the math happens. I wrote this equation on the board. Maybe you didn't believe it was this simple, but this is how we build it, and this is how we run it in software. Very, very straightforward. The cool thing being, I can add as many independent variables as I want, and it still gives me all the parameter estimates. We kind of ignored the standard errors there, which are necessary for the tests, but we're not going to talk about it here. We talked about how we do the built-in commands for the regression output for multiple linear regression. All 3 of these were the same as for the simple linear regression. We talked about building the ANOVA components by hand. Again, very straightforward using software. Some of these calculations would take potentially many, many hours, weeks by hand. And in software, they're just very straightforward. Building the critical value and p-value for a test that, while we could kind of get it from the pieces in R doesn't directly calculate the overall test of regression when I have multiple independent variables. So we talked about finding the critical value for that and the p-value for that. And then we talked about doing R-squared, adjusted R-squared, and fitting our nested regression models with a full model and a nested set in there. So, ladies and gentlemen, thank you so much for sticking with me through this video, and I will look forward to catching you in the next one.